Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to describe polar coordinates and how to use them to graph various points. So I'm going to start this though by talking about Cartesian coordinates. So if we were to think about the point like maybe the point 3, 1 on a Cartesian coordinate system, and again the point 3, 1, this is an x value and a y value. If I go ahead and plot that point on this coordinate system, that would be, let's see, 3 over 1 up, pretty well exactly right there. Now, polar coordinates are just an alternative way to graph. And instead of an x and a y, in polar coordinates what we give is an r and a theta, where the r is the distance from the origin to the point. So in the example that I have just drawn, r is going to be this distance in red. Whoops. Red. So in this example, there's r. The angle theta is the angle with respect to the positive x-axis. Now again, think back to trigonometry and mathematics in general. When you're given an angle, typically, unless you're told otherwise, they are measured with respect to the positive x-axis with counterclockwise positive. So again, plus 45 is up in quadrant 1, plus 90 is here, plus 180. Now when you go the other way, an angle something like maybe about here, that's minus 45, and down here would be minus 90 and so forth. So just remember when you're graphing or doing anything with angles, unless you're told otherwise, angles are measured with respect to the positive x-axis with counterclockwise positive. So this point here was the point 3, 1. And I'm going to go ahead and draw some distances here in green. The x value is this distance here. And in this case, x is equal to 3. The y value is this distance, and in this case, y is equal to 1. And one of the things we want to be able to do with polar coordinates is go back and forth between polar and Cartesian. So in this example, all right, we're looking at a right triangle here. There's several equations we can write. First one I'm going to write out is this. The cosine of the angle theta is equal to x over r. Because x is adjacent to theta, r is the hypotenuse. Or in functional form, the cosine function on a circle centered at the origin is defined as the ratio x over r. Sine theta is equal to y over r. And in addition to that, we can write out the Pythagorean Theorem relationship for this triangle, which is x squared plus y squared equals r squared. So basically, these three equations here are what will allow us to go back and forth between polar and Cartesian coordinates. So in this example, I can actually calculate the r easy enough by Pythagorean Theorem. So we're going to have 3 squared plus 1 squared equals r squared. So this is going to read 9 plus 1 equals r squared. So r is equal to the square root of 10, which is 3 point something. Right. Theta we can find basically using any trig function we want. I'm going to go ahead and do this. The tangent of the angle theta is equal to y over x, and that's going to equal 1/3. So theta is going to be the inverse tangent of 1/3. I'm going to go ahead and take a moment here and ask my helpers here. Somebody give me inverse tangent of 1/3, please. .4. Okay, 18.4 degrees. Would somebody give me this in radians, please? And the way you get this in radians is take the 18.4 degrees, and we're going to multiply this by pi over 180, and that's radians per degree. .32. Okay, thank you. So that's approximately 0.32. So what we've discovered here is the Cartesian point 3, 1 can be expressed in polar with an r and a theta, and that would be square root of 10, 0.32, radians. Typically, when you express angles in polar, you typically express them in radian form. Right. Now, I'm going to go ahead and pause this and chat about some other details about polar. Okay, folks, so I paused and I'm back, cleaned it up. We're going to take a look at the point 2 pi over 6 in polar. So again, in polar, this angle pi over 6 would put us up into quadrant 1. I know that pi over 6 is 30 degrees. So, and the r was 2. So the polar coordinate here is this point where this distance is 2 from the origin. So one of the things we want to be able to do now is convert this back to Cartesian. So we've got a pi over 6 angle. And I'll go ahead and just use a straight edge here, or no straight edge. This distance is x. This distance is y. And to convert this to Cartesian, all we got to do is calculate x and y, and it's a pretty easy calculation here. So the cosine of pi over 6 is equal to x over 2. So x is equal to 2 times the cosine of pi over 6. Now the cosine of pi over 6 is root 3 over 2. So that's equal to the square root of 3. This is, I don't know, 1.3 or 1.4 something. Y we can find by using the sine function. The sine of pi over 6 is equal to y over 2. And if we solve this for y, we get 1. So the Cartesian coordinates here would be the point root 3, 1. Now, polar graphs have one big difference between polar and Cartesian is what I would just call uniqueness. All right, so this point here in Cartesian, root 3, 1, this is the only way to express this point right here in Cartesian format. However, in polar format, that's not quite true. There's actually many, many ways to express this same point in polar, and I'll talk about some of the other ones. So if we were to take pi over 6 and add another 2 pi to it, that would go all the way around, and we'd be at the exact same point. So the point 2 pi over 6 plus 2 pi gets us to exactly the same point. I guess I'm going to go ahead and write that as 2, and this should be what, 12 pi over 6, 13 pi over 6. These 2 points are equivalent. They put you at exactly the same spot in the circle. I could add 2, I could take the point 2 and a 13 pi over 6, add another 2 pi, would put me at exactly the same spot. So in general here, I could say that the point 2 pi over 6 plus 2 pi k, where k is going to take on integer values. Actually, k could be, in this example, 0, plus or minus 1, plus or minus 2, etc. Any angle that lands me at this point correctly describes this position in polar. Now, generally, distances are positive. However, in polar coordinates, this r does have a meaning for a negative value. And here's the meaning for r for a negative value. If I were to look at the angle from here to here would be pi, and if I tack on another pi over 6, that would put me here. This point would be the point 2, and then it'd be pi plus pi over 6, which is 7 pi over 6. So the point 2, 7 pi over 6 puts me here in polar. A negative radius basically means go the other way, I guess, for lack of a better way to put it. So if I go to the angle 7 pi over 6 and I use an r of negative 2, that would put me back here. So this point, alternatively, can be described as negative 2, 7 pi over 6. Also, if I take the negative 7 pi over 6 and I add any multiple of 2 pi to it, that would put me here angle-wise, where the negative radius would put me here. So in general, negative 2, 7 pi over 6 plus 2 pi k is an alternative way to describe this point. So you can see that in Cartesian format, this point is unique. Root 3, 1 is the only set of coordinates that put you exactly at that point on the plane. But in polar coordinates, there's, I guess for lack of a better way to put it, a set of coordinates that will put you there. One of those sets is here. R equals 2. Angle can be pi over 6. Oh, I see when I wrote that, I forgot to tack the... Oh, I did right here. R equals 2. Angle equals pi over 6, or any multiple of 2 pi tacked on. Alternatively, we could use basically this as our starting angle, 7 pi over 6, as long as we use a negative value for r, which basically means go to the other way, to here. And then we can tack any multiple of 2 pi onto that, would alternatively put me at the same point. So the purpose of this video is just give you a general flavor for what polar coordinates are and how to graph points in polar, and a little bit about how to go back and forth between Cartesian and polar. And I think what I'll do is I'll stop this here and save my examples for another video. Have a great day.